we're unpacking the absolutely crucial and, honestly, often misunderstood differences between high flex and continuous flex cables.
So why do multi-million-dollar automated machines just suddenly fail? Well, the culprit is usually hiding right there in plain sight, a ruptured cable. And the reason that cable ruptures, causing all this massive, expensive downtime, is usually because engineers casually use these two terms, high flex and continuous flex, interchangeably, and they really shouldn't.
Here's our quick roadmap for this explainer. 1. The core conceptual difference. 2. When to use which. 3. Inside the manufacturing process. And 4. The threat of corkscrewing. We're diving all the way from macro concepts down into the microscopic logic of the wires themselves. Let's get right into it. Section 1. The core conceptual difference. Physical pliability versus operational endurance.
Okay, let's dive into this. We need to establish right off the bat that these two cables rely on entirely different metrics of motion. High-flex cables focus purely on physical pliability. It's about an aggressive bend radius and being able to manually maneuver the cable through incredibly tight, complex spaces. Continuous flex? Completely different animal. It focuses on the application environment, specifically surviving relentless, 24/7 automated motion. It prioritizes pure endurance over manual bendability.
The contrast becomes super clear when you look at the specs. High flex is built for intermittent bending, usually rated for 1 to 20 million cycles. But continuous flex is built for automated, non-stop stress, engineered to withstand well over 10 million cycles. To put that into perspective, that's literally like aggressively bending a paper clip every single second for 4 months straight without it snapping. Crazy, right? And as you might guess, their internal geometries reflect these vastly different jobs.
Section 2. When to use which. Real-world application environments. So, let's get practical. When exactly should you spec each type to avoid those catastrophic failures? Well, you're going to want to choose a high-flex cable when you're routing through extremely tight spaces or really sharp corners. This is for applications that move frequently, sure, but only intermittently. Think of like a medical imaging panel getting manually adjusted by technicians a few times a day. If your system requires multi-axis bending and space is at an absolute premium, the pliable nature of high flex is for sure your best choice. On the flip side, you absolutely must choose continuous flex if the cable is going inside automated drag chains or CNC machines. We're talking about machinery running 24/7 at incredibly high speeds and accelerations. Here, your primary risk isn't navigating some tight corner. It's the sheer mechanical fatigue from millions of identical, repetitive, linear movements. Continuous flex is basically mandatory to survive that kind of relentless punishment. Quick aside here, though. In highly demanding robotic manufacturing, premium manufacturers will sometimes design high-end cables that actually boast both capabilities, letting them handle the most extreme, complex robotic environments you can imagine. But that's a specialized case.
Section 3. Inside the manufacturing process, the engineering logic.
So, we're dropping down to the micro level now to ask a critical question. How exactly are these two differently manufactured on the inside? Well, as we're about to see, high flex cables are designed to bend easily, while continuous flex cables are intricately engineered to survive immense mechanical stress without destroying themselves from the inside out. Let's start with the conductor stranding itself. High flex uses ultra-fine wire strands. We're talking 36 to 40 AWG. Because they're so fine, they slide super easily against each other, making the cable incredibly pliable in your hands. But look at continuous flex. It uses slightly thicker, optimized strand counts, around 30 to 34 AWG. And this is precisely calculated, because if the strands are too fine, they'll actually birdcage, which is basically a disastrous bad hair day where the wires bunch up and snap under rapid automated acceleration. And this brilliantly illustrates the core architectural difference. High flex layers its conductors in simple concentric circles around a center point. It's really efficient for saving space, but those inner wires can crush under millions of automated cycles. Continuous flex, instead, uses this heavy-duty bundle-within-a-bundle design, twisting subgroups of wires around a central tensile strength member, something tough like Kevlar. Even the internal lubricants are completely different. High flex can usually just rely on standard talcum powder, chalk, or maybe a thin fleece wrap for its occasional bending. But continuous flex? It requires specialized heavy-duty lubricants, low-friction fleece, or even extruded inner jackets.
It literally needs these robust materials just to survive the massive internal friction and heat generated by non-stop operations.
And all of this internal architecture builds up to the outer jacket. For high flex, the jacket is often tube extruded, so it's blown onto the cable pretty loosely, or made of elastic silicone for maximum softness. Continuous flex is pressure extruded. The jacket material is violently forced under high pressure right into every single gap between those internal conductors. This forms a solid, rigid profile that absolutely locks the internal components in place so they cannot shift around during movement.
Section 4. The threat of corkscrewing. Destructive failure points.
Okay, here is the climax of our macro to micro journey. So the absolutely crucial point in preventing failure is understanding lay length, which is also known as the twist pitch. Simply put, lay length is the linear distance it takes for a single wire strand to complete one full 360-degree rotation around the cable core. This simple winding distance dictates everything.
A loose twist pitch, which you'll find in high flex, covers a long linear distance. It feels soft, it feels pliable. But if you bend it repeatedly in a machine, the outer wires stretch and the inner wires compress, causing them to actually physically migrate. Contrast that with the very tight lay length of continuous flex. This aggressive twisting over really short distances acts exactly like a mechanical spring. A wire quickly shifts from tension to compression in just a fraction of an inch, completely neutralizing those dangerous mechanical bending forces.
And if you don't neutralize those forces, you get corkscrewing. This is a highly destructive failure where the internal wires, constantly seeking the path of least resistance under bending stress, literally migrate. They bunch up, they aggressively knot together, and eventually they rupture and crush right through the outer jacket. It is totally fatal to the cable, and by extension, fatal to your machine's uptime.
To kind of sum up this whole engineering philosophy, just consider this quote. Because of that tight lay length and pressure extruded jacket, this structural integrity allows the cable to survive tens of millions of rapid, repetitive cycles without corkscrewing or breaking. Ultimately, it's that rigid, locked-in structural integrity on the inside that guarantees survival on the outside.
As we wrap up this explainer, I really want to leave you with this final thought. Take a look at the automated machinery you're trusting your business to. Are you sacrificing structural integrity on the inside just for a little pliability on the outside? It's a multi-million-dollar question definitely worth asking. Thank you for joining me on this deep dive, and as always, keep questioning how the world around you works.